velocity and acceleration and distance graphs. You should already be familiar with the formula v equals v0 plus at. That is, the velocity is equal to the initial velocity plus the acceleration times time. You could consider it the definition of acceleration. You should also be familiar with x as the symbol for distance. Velocity times time equals distance. Now, let me get this one out of the way. Velocity times time equals distance. But if it's a constant velocity, it might as well be the initial velocity times time. But you could have a starting position x0. Now we have a change in position. But what if you accelerate? Then you'll go an extra distance, and that extra distance is 1/2 at squared. So here's our second formula, like that. X equals x0 plus v0t plus 1/2 at squared. These formulas can be shown on graphs. I'm going to do that at this time. First, for this case, acceleration is 0 on these three graphs. This is a graph of acceleration, a graph of velocity, and a graph of distance, putting x on the y-axis. If the acceleration is 0, the acceleration is 0. That's it. The acceleration is 0. Nothing we can do about that. The velocity, if the acceleration is 0, will be constant. Constant velocity, staying constant the whole time. No change. And here, if there's a constant velocity, then the position will change at a constant rate, like that. Now, I want you to notice that the velocity is the slope on that graph. How quickly is the position changing? I'll now draw a second case. Acceleration is constant, like maybe the acceleration is 5 meters per second, or maybe in the case of gravity, 10 meters per second squared. If the acceleration is constant, the acceleration is constant. Constant. If the acceleration is constant, then the velocity is constantly changing. The velocity is constantly changing. Now I want you to notice, the faster the acceleration is, the bigger the velocity is changing, the quicker it's changing. So that means that the acceleration is the slope on that graph. On the last graph, we have a velocity that starts off at 0, so no distance is covered. But then as time goes by, the slope here, because the velocity is still the slope will increase. So that's what you get, a parabola. We should have predicted this already, since it was 1/2 at squared for accelerated motion. What about over here? Is the acceleration still the slope? Yes, but in this case, the slope was 0. Consider now a case in which the acceleration is a constant 2 meters per second squared. The velocity starts off at 5 meters per second, and the initial position is 3 meters. All these initial conditions, how would they look on the graphs? Well, in the case of acceleration, it's just a constant 2, constant acceleration. In the case of velocity, you would not start at 0, but you would start with an initial velocity of 5 and increase your velocity at 2 meters per second each second. So it would still be a constant slope, constant acceleration, but you would start at your initial velocity. Now, what about this case x? We have an initial position of 3. I'll mark that here, xo. And we should expect a parabola, but we have an initial velocity, which means we'll actually start with a slope, which will curve into a parabola. So it starts with a slope and curves up. Let's describe these with formulas. The velocity formula, well, that's v equals v0 plus at. That's v equals y-intercept of 5 meters per second plus slope 2 times x time. So that's the acceleration right there. On the x formula, it's x0, which is 3, plus v0t, 5t, plus 1/2 at squared, that's 1/2 2t squared. As a summary, I'm going to draw these three graphs. First, I'll draw the graph and you tell me what it is. There. A straight line on the distance graph. Well, that must mean we have a constant velocity. But, what's this? That little spot right there. That dot. What is it? Right there! That must be the initial position. Aha. So this perspective, this graph, could be described as x0 plus vt, where the velocity is constant. So, there's that. That's the formula for this graph. X equals x0 plus vt. Alright, here's another one. Alright. On a velocity versus time, we have some starting position and a slope. There is acceleration. The velocity is changing. That's the initial velocity, so we could describe this one as velocity equals initial velocity plus acceleration times time. The acceleration is the slope. Here, the velocity is the slope. And in the third case, I'm drawing this parabola. It looks like we start with an initial position, x0. So our formula x would be x0, but notice there's no initial slope, so there's no initial velocity times time, but there is acceleration, plus 1/2 at squared. There's your formula, as curvy as it is.